The Key Refinery. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're exploring an unsung hero of modern cryptography, the Key Derivation Function, or KDF specifically. We'll dive into HKDF, the standard used in TLS 1.3 and many other protocols. We've talked a lot about how to create a shared secret, but how do we turn that single secret into the multiple, highly secure keys needed for a real-world connection? That's the job of the KDF, the cryptographic key refinery. The problem: from one secret to many keys. A key exchange protocol like ECDHE gives us one shared secret, typically the x-coordinate of an elliptic curve point. But a secure session needs multiple keys. We need one key for the client to encrypt data, a separate key for the server for encryption, another key for the client's message authentication, and yet another for the servers. Why can't we just chop up the shared secret? The reason is that a raw shared secret is not guaranteed to be uniformly random. It may have biases or patterns. Using parts of it directly could leak information. We need a way to refine this raw material into pure, independent cryptographic keys. What is a key derivation function, KDF? A KDF is the tool for this job. Think of it as a cryptographic refinery. Its purpose is to take some initial, potentially non-uniform secret, called the input keying material, or IKM, and transform it into one or more strong, independent, and uniformly random secret keys suitable for cryptographic operations. Just as an oil refinery takes crude oil and produces different, pure fuels like gasoline and diesel, a KDF takes a raw secret and produces different, pure cryptographic keys. Meet HKDF, the modern standard. The modern standard for this process is HKDF, which stands for HMAC-based Key Derivation Function, defined in RFC 5869. It's the KDF of choice for TLS 1.3, Signal, WhatsApp, and many other modern protocols. Its popularity comes from its simplicity, strong security proofs, and its clever two-step design: extract and expand. This two-phase process is what makes it so robust and flexible. HKDF Step 1. The extract phase. The first step is to extract. The goal of this phase is to take our initial secret, the input keying material, or IKM, and concentrate its entropy into a single, high-quality pseudorandom key. The IKM might be a Diffie-Hellman shared secret, which could have some biases. The extract step smooths out these biases and creates a cryptographically strong key of a fixed length. This is done using the HMAC algorithm. The formula is PRK equal operator HMAC, salt, IKM. The output, PRK, stands for pseudorandom key. The role of the salt. The formula includes an optional value, called a salt. A salt is a non-secret, random value. Its purpose is to ensure uniqueness. Even if the same IKM is used in two different contexts, using a different salt for each will produce a completely different final key. This is a crucial feature for domain separation, preventing a key from one protocol from being accidentally reused or confused with a key from another. In TLS, this salt is often derived from the initial handshake hashes. HKDF Step 2. The expand phase. Once we have our strong pseudorandom key, or PRK, from the extract step, we can proceed to the expand phase. The goal here is to take that single, high-quality key and use it to generate as many bytes of keying material as we need. This is an iterative process. It repeatedly uses the HMAC algorithm, feeding in the PRK along with a counter and an optional info string, to produce a long, continuous stream of cryptographically strong bytes. This output stream is called the output keying material, or OKM. The role of the info string. The info parameter in the expand step is another crucial element for security. This is an optional string that binds the generated keys to a specific context or application purpose. For example, in TLS 1.3, different info strings are used to generate the keys for encrypting handshake messages versus the keys for encrypting application data. This ensures that the key for one purpose can never be confused with or used for another purpose, even though they both came from the same initial secret. It is another layer of domain separation. Visualizing the expand phase. This diagram shows how the expand phase works. The PRK is used as the key for the HMAC function. The algorithm begins with an empty string and the info context. It hashes these together to get the first block of output. This output is then fed back into the next iteration to generate the subsequent block, and so on. This chain ensures that every byte of the output depends on all the previous bytes, creating a secure, pseudorandom stream of output keying material, OKM. From OKM to final keys. At this point, we have a long stream of secure bytes called the output keying material. The final step is simple. We just chop up this stream into the sizes we need for our symmetric keys. For example, if we need two 128-bit 16-byte AES keys and two 256-bit 32-byte HMAC keys, we would take the first 16 bytes of the OKM for the first key, the next 16 bytes for the second key, the next 32 for the third, and so on. Because the OKM is cryptographically strong, we can be confident that each of these sliced keys is independent and secure. The full HKDF process. This diagram shows the complete, end-to-end HKDF process. It's a beautiful, two-stage pipeline. The potentially weak input keying material, our shared secret, is first purified and strengthened by the *extract* step into a single pseudorandom key. Then, this strong key is used by the *expand* step to generate a long stream of output keying material, which is finally sliced into all the specific encryption and MAC keys required by the application. This is the complete journey from one raw secret to many refined keys. A practical example. HKDF in TLS 1.3. Let's connect this to the real world with TLS 1.3. At the end of the ECDHE handshake, the client and server have a shared secret point. The x-coordinate of this point becomes the input keying material IKM for HKDF. The protocol then uses HKDF multiple times with different salt and info values to derive all the keys it needs. First, it derives a set of handshake secrets to encrypt the final part of the handshake. Then, from those, it derives the application traffic secrets that are used to encrypt the actual web data. This layered approach, made possible by HKDF, is a key part of TLS 1.3's security. Why not just use hash secret? A common question is, why go through all this trouble? Why not just use a simple hash function like SHA-256 to derive keys? The reason is that standard hash functions are not designed for this purpose. HKDF's HMAC-based construction provides much stronger security guarantees. For example, it's not vulnerable to length extension attacks that can affect simple hash constructions. Using a purpose-built tool like HKDF is always the right approach. HKDF is specifically designed to be a secure key refinery, whereas a hash function is just a general-purpose fingerprinting tool. Conclusion. In conclusion, a key derivation function is the essential bridge between establishing a shared secret and using it for secure communication. The modern standard, HKDF, provides a robust, two-step process to do this. The extract step takes a raw secret and purifies it into a single, strong master key. The expand step then uses that master key to generate multiple, independent session keys for different purposes. This extract then expand paradigm is a simple but powerful construction that has become a fundamental building block of modern, secure protocols like TLS 1.3. Final thoughts. The next time you see the padlock icon in your browser, you can think of the hidden cryptographic symphony at play. ECDHE creates the initial secret note, but it's the unsung hero, HKDF, that acts as the conductor, transforming that single note into the rich harmony of different keys needed to protect your data. Understanding the role of the KDF is essential to appreciating the full depth and elegance of modern security protocols. Thank you for your attendance. Please consider subscribing to the channel.